you have a box, if you have some box full of gas, then you can measure its volume. Okay, so volume measurement is a mechanical thing. So you can measure its volume. You can measure what are the force acting on the surface of this box. So you can measure a quantity called pressure. So these are the mechanical coordinate or mechanical properties of the system. So in thermodynamic properties, so some kind of properties are mechanical properties. So these are the mechanical properties. If you have a wire, spaced wire, what you can measure the length of the wire, and you can measure what are the force acting on the wire, that is the tension of the wire. So these are the force acting on the wire, tension of the wire. So these are the mechanical properties of the wire. Similarly, if you have a magnet, you can measure what is the field acting on the magnetic field acting on the magnet and what is its magnetization. So these are the mechanical properties. Now in thermodynamics, we also need to know what are the thermal properties. The notion of hot and cold, people has already had, but they do not know how to quantify the notion of hot and cold. So there comes the zeroth law of thermodynamics. Okay, so zeroth law of thermodynamics gives you an idea how to. So we have discussed these things in details in the last class. So I will just briefly mention that because I need that in order to go to the first law of thermodynamics. So here comes the zeroth law of thermodynamics. Here comes the zeroth law of thermodynamics, which tells you that if you have a system C which is in thermal equilibrium with two systems A and B, which are not in, which are separated by some adiabatic wire. Okay, so a system C in thermal equilibrium with the system A and system B, which is separated by adiabatic wire, which is not in equilibrium with each other initially. Then the zeroth law says that the A and B must be in equilibrium. Okay, so let us assume that this is, and we need some mathematical calculation and show that if the system C is described by thermodynamic coordinates, say xc and yc. A is described by thermodynamic coordinate HA and YA, and B is described by thermodynamic coordinates XB and YB. Then zeroth law of thermodynamics tells you that if ABC are in thermal equilibrium, there must be some function HA, which is a function of XA and YA, which is equal to some function HB, which is a function of XB and YB, which is equal to some function HC, which is the function of XC and YC. So these equations we have proved from the zeroth law of thermodynamics, and in the last class. So this is what you have. Zeroth law of thermodynamics, mathematically start mathematically, and you will be able to obtain such a relation. That if three systems A, B, C are in thermal equilibrium with each other, the systems are described by simple system, two thermodynamic variables, say x and y. Then there should exist a function HA, HB, and HC, such that these functions are equal, same. And we define this quantity as the empirical temperature. So you understand the notion of hot and cold. We can quantify using this zeroth law of thermodynamics. So zeroth law of thermodynamics gives us a way to quantify our idea about hot and cold. in terms of thermodynamic coordinates. Okay, so I introduce the concept called temperature, which actually tells you whether two systems are in thermal equilibrium or not. So this is the objective of temperature. And we have also, zeroth law of thermodynamics also tells you that. Let us try to understand this equation more closely. So let us assume a simple experiment. Let us assume that I have a big heat bath. Okay, some heat reservoir, some water at a given temperature. A bucket of water at a given temperature. In this bucket of water, I can imagine a system A and I can imagine a system B, which are in thermally contact with this bucket of water. This heat, the heat reservoir. So I have a big heat reservoir. In that heat reservoir, I imagine two systems A and B. This system A and B could be very different. A is given by A is described by thermodynamic coordinate xa and ya, and B is described by thermodynamic coordinate xb and yb. So this system A and system B are in thermal equilibrium with this heat bath. So this heat bath is your system C. So that tells you that system A and system B are in thermal equilibrium with each other. So if system A and system B are in thermal equilibrium with each other, then there should exist an equation like this. And if I plot this equation for system A, so this will be my xa coordinate, this will be my xb coordinate. I will see that all possible values of xa and xb, which are in thermal equilibrium with this heat bath, will fall on a curve. Okay, so if I change the temperature of this heat bath, if I heat up this heat bath, it is a water bath. If I heat up this heat bath, I will obtain another curve. Similarly, for system B, I will have a line which corresponds to a particular temperature for system B, a particular thermal equilibrium condition for system B. That line would be very different from system A. System B would be very different from system A. But the point is that you will have these lines. So there will be a direct one-to-one correspondence between this line and that line, and this line and this line. We can say that all states on this line is in thermal equilibrium with all states on this line. Similarly, all state on this line is thermal equilibrium with all state on this line, because all states on this line is thermal equilibrium with this heat bath, which is in thermal equilibrium with all states of this line with system B. So this is actually the consequence of zeroth law of thermodynamics. And as we have this zeroth law of thermodynamics, we have the idea how to quantify this quantity temperature. So this is a thermodynamic coordinate. Now we need to assign some numbers with this thermodynamic coordinates. We want to measure this thermodynamic coordinates. We want to compare this thermodynamic coordinates. We want to assign some numbers with this thermodynamic coordinates. And we also discussed how to obtain the universally acceptable scale for this quantity called temperature. That is called the ideal gas scale. We have discussed what is the importance of ideal gas scale and why is so we have ideal, which is the universally accepted scale for measuring, for assigning numbers to this quantity temperature. Right? So this is what we have discussed in the last class, and this is the idea we will proceed further. Okay. So after zeroth law comes the first law of thermodynamics. Let us go to the first law of thermodynamics. First of all, let me write down the statement. Then I can try to explain the statement, and that may take several classes. Okay. Because you need some mathematical understanding, mathematical background to understand, to do actual calculation, actual understanding, to have actual understanding about the statement. So, it tells you that if a system which is adiabatically isolated changed a system which is adiabatically isolated is changed by what the what the quantity of what is only a function of initial and final state of the system. So this is the statement. Let us try to understand this statement. So it tells you that you have a system which is adiabatically isolated from the surroundings. Now you change the state of the system from one particular state to another particular state by doing some work on the system. So what? So we need to do what? We need to understand how we can do work on a thermodynamic system, how we can calculate what is the amount of work. So that will be the topic of today's discussion. Maybe next year's discussion. So this is the important thing, actual calculation. So we need to go slowly. Okay, so this tells you that first law of thermodynamics tells you that if you change the state of a system which is adiabatically isolated from the surrounding, from an initial state to final state by doing some work. So what is the amount of work? The amount of work is only depend, the amount of work done on the system or by the system only depend on the initial and final state of the system. It will not depend on anything else, it will only depend on the initial and final state. So it says that if you know that a system is adiabatically isolated from the surroundings and it goes from an initial state to a final state. Okay, so if you know the initial state, if you know the final state, you know what is the amount of work done on the system or by the system, whatever, the amount of work you know. So from the knowledge of initial and final state, you know what is the work done on or by the system. Okay, so this is the statement of first law of thermodynamics. We will, it has several interesting consequences. in the context of heat transfer, conservation of heat, conservation of energy, etc., etc. So we will discuss. We will slowly understand these things. But this is the statement of first law of thermodynamics. Okay. So let us pictorially try to understand what this statement means. Let us assume that we have a thermodynamic system. We have a cylinder with a piston here. I put some weights on the piston so that it has a certain amount of pressure, and last class I have discussed how you can calculate it. The simple description of a system. System of gas enclosed by a piston. Put some weight on the piston, so you know what is the pressure on the system. It has a pressure, it has a certain volume, and this is adiabatically isolated from the surroundings. So these are adiabatic walls, and also this piston is adiabatically isolated. So you cannot interact thermally with the surroundings. So this is the system. Now you need to do work on the system. Okay, so there are several ways you can do work on the system. Okay, you can put some more weight on the piston. So this piston will go a little bit down. You can remove some weights from the piston. So this piston will go a little bit up. You can fix a spring here and pull the spring from the downside. So there are several ways that you can do work with this system. Okay. There are several ways you can change the volume of this system, and changing the volume which corresponds to a work done on the system. So there are several ways you can do. So this first law of thermodynamics tells you that so there are two coordinates PV. Okay. The system, the state of the system is specified by a specific value of P and a specific value of volume V. So this is how you state the specify the state of the system. Let us assume that at a given time the system is in these states with a value. So this is the PV diagram. So with PI and VI. And at a final at some later time, the system goes to a different state with some PF and VF. You do some mechanical work, you do something mechanical to change the state of the system. Okay. Then this zeroth law of thermodynamics tells you that you do not need to know if the system is adiabatically isolated from the surroundings. The first law of thermodynamics tells you that you do not need to know what is the path that connects these 2 points P1, PI and PLP. What is the path? So there are several paths. You can take the system from one particular initial state to a final state in several different ways. There are thousands of, infinite number of paths possible in which you can take this. You can do this things. But the first law of thermodynamics tells you that the work done will only depend on PI, VI and PLP. So this is the statement of first law of thermodynamics. We will understand more about the statements in the coming lectures. But one thing you understand that in order to understand the meaning of this statement, you need to be able to calculate the work done from this point to if the system goes from this point to this point in different paths. You should be able to calculate what is the work done. Otherwise, you cannot do anything with this statement. This is a meaningless statement if you cannot calculate the work done in different paths. Then only this statement is a meaning. So our objective will be to understand, will be to learn how we can calculate work done on a thermodynamic system. Okay, so this will be our next objective. And then we will come to the first law of thermodynamics and try to understand its consequences. But in order to understand its consequences and do some realistic calculation, what we need to know, we need to understand, we should be able to calculate the work done by a thermodynamic system. what is the, I mean, how we can calculate the different kind of work done by thermodynamic systems. So that will be our objective today, or maybe for the next class also. That you are doing. Okay, so before going to the work done calculation, we need to know some basic, very basic mathematical theorems about differential calculus. Okay, and one thing I haven't told you that all these thermodynamic variables can be categorized into two kind of variables, intensive and extensive. I think you have all know that. What are the intensive variables? So thermodynamic coordinates. There are two kinds. It could be a intensive or extensive. You know these things, right? So there needs to be intensive. You might take a thermodynamic system. So it's explained by some thermodynamic coordinates x, y, z, etc., etc. It has some thermodynamic coordinates. Now, in this thermodynamic coordinates, I can categorize them as intensive or extensive depending on their properties. So what I can do, I can make the system half. In two halves, I can split the system. Some of the coordinates will be divided by a factor of 2, half factor, and some of the coordinates will remain same. The coordinates which remain same, if I split the system into two halves, those are the intensive coordinates, and which is divided by a factor of the coordinate which is divided by a factor of half, that will be extensive coordinate. For example, in a gas system, the thermodynamic coordinates are P, V, and T. Now I can simply imagine that if I divide the system, the volume is divided by a factor of 2, but the temperature and pressure remains same for both the systems. So in this case, V is the extensive coordinate and P and T are intensive coordinate. Okay, so you know these things, so I am not going, I do not want to spend time on these things. And there are several interesting consequences of this intensive and extensive coordinates. We will see in future that something interesting is there, but yeah, so that will come in future. So mathematics. So we will actually understand and learn and prove two theorems for partial differential calculus, which we will use quite often. So any question? Any question from this part of the discussion? No. Okay. So let us go to this mathematical theorems for partial differential calculus. Let us assume that we have a, so this is what I am starting, this is the starting point. We have a one-dimensional function f of x. So one-dimensional function means that the function is dependent only on one variable, and we can have a plot. X-axis I can call it a x-axis and y-axis a fx-axis, and in this plot the function will be represented by some kind of a line. Okay, so this function can be pictorially represented in a plot in this kind of a line. So this is the definition of a one-dimensional. Let us assume that this is a particular point x on this function. This is a particular point x on this function. Now the question is, if I change x to x plus dx, let us assume that another point is here, which is dx distance away from x. So this is the point x plus dx. How the function is changing? What is the change in the value of this function? So that is the question. This is a very simple question, and probably you know the answer of this question. So the function f at x plus dx. So the change in the function df should be equal to the function x at point x plus dx minus function of x. So this is the value of function at this point. This is the value of function. This is the value of function. This is fx, and this is fx plus dx. So this is the change in f as I go from x to x plus dx. So you have learned about Taylor series, right? Have you learned about Taylor series?
Yes, sir.
Okay. So if you know Taylor series, then you can simply write down this part as times dx plus the higher order terms. Okay, plus the terms which involve dx square, dx cube, dx to the power 4, etc. Now this dx is, if this dx is infinitesimally small, then you can actually ignore this higher order parts because they will contribute less and less. So you can actually ignore the higher order terms. So df is basically del L by del x times dx. So in this case, actually, this is your, I mean, del F by del x is the slope of this graph, and this is your delta x. So this is basically this times x. So this is how you can calculate the differential change of a function if the argument of the function changes differentially. So this is for one-dimensional function. You can easily generalize it for n-dimensional function. If you have a 2D function, where f is a function of x and y, two variable, and your x and y. Okay, let us draw the picture. So you can draw a two-dimensional function on a three-dimensional plot. Let us assume that this is my x-axis, this is my y-axis, and this is my fxy. So a one-dimensional function is represented by a line on a two-dimensional plane. A two-dimensional function will be represented by a surface, some kind of a surface on this. Okay, so for a given value of x and y, there will be a value of function fx and y that will be a point on this surface. So this is a two-dimensional function. So now I can ask the same question. Let us assume that I am at this point, which is categorized by quantified by the coordinate x and y. If I go infinitesimally away from this point to another point, which is the coordinate of that point is x plus dx and y plus dy. Then what is the change in df? So this is the question. What is this df? So this is your df. Okay, so the answer is simple. The x, so this is the problem. X goes to x plus dx and y plus dy. So what is your df? What is the change in that function? That will be f x plus dx, y plus dy minus f of xy up to the linear order in dx and dy. This can be written as del f by del x at constant y dx so this will be your df up to linear order. Okay, so you will have other terms where you can have dx square, dy square, or dx dy, this kind of cross term. But as long as we are assuming that this dx and dy are infinitesimal small, you can ignore those terms. So now you can see that it is different from the previous equation. In the previous equation, I wrote df by dx times dx because f was the function of x only. But in this case, this f is not a function of one variable; it's a function of two variables, x and y. That's why I have introduced partial differential of f with respect to x for constant y. Okay, so this is the difference from previous equation to this equation, and this is a very important difference. Okay, so you can pictorially visualize this quantity. I mean, these partial things are sometimes little confusing, so you need to understand this quantity carefully. So, what is this del f by del x at constant y? So, let us assume that this is the surface. Okay. This is the surface of fxy. Now let us assume that this is a particular point on y at a constant value. Okay. So y equal to some constant is represented by a surface, by another surface which is parallel to this fx plane. So this will be a parallel surface. Let us assume that this fx plane is the plane of this board, y is coming out of this board, so that will be a surface parallel to this plane. Okay. Now there is one surface which is represented by this function fx and y, and there is another surface which is parallel to this f and x plane. Then these two surfaces will cut each other at a particular line. So that line will be an equation of x only. Okay, so I can differentiate that line with respect to x. So this is that differentiation. Differentiate x, f with respect to x for a constant y. So you understand this, right? If anyone has any confusion, then I can again explain it.
Sir, please repeat once again.
Huh?
Sir, repeat once again.
Repeat, okay. Because this is important to understand. Let us draw this picture in a different form. So that will give you some more. Let us assume that this is my x-axis, this is my fxy axis, and my y-axis is coming out of this plane. Okay. So fxy, my y-axis is coming out of this line. This is perpendicular to this axis. It's coming out of this plane. Now fxy in this three-dimensional space will be represented by a surface. Okay. So this is my y-axis. It's coming out of this plane, and fxy is a surface represented by a surface on this three-dimensional coordinate system. Now, if I take a fixed value of y, so that will correspond to another surface, another plane, which is parallel to this plane, x and f plane. So that plane will cut the fxy surface at a line. So two planes cut each other at a line. So that line will be a function of x where y is fixed. So you are taking, so this quantity is basically taking the gradient of that line at a given point. So this is the definition of, I mean, this is how you can define a partial derivative. You have the geometrically, this is, you can visualize the picture in this way. So you have a line. So you take a plane which is parallel to this plane, which is your y equal to some constant plane. Now that plane will cut your this fxy surface, which is a surface like this, which is coming out of this, and surface like this, which is coming out of this plane of the board. And this parallel plane will cut this axis, this surface at a curve. So that curve has a gradient along this x. As a slope, not gradient, as a slope for each value of x. That particular slope is the partial derivative of this two-dimensional function f with respect to x at a given value of y. So that is the definition of partial derivative of f. Okay, now if we have some ND functions, this is simple and just for completeness I am writing this. So this will be a function of x2 up to xn. This df will be this will be equal to the sum of all these things del f by del x1 when all other coordinate x2 to xn are fixed dx1 del x2 when all other coordinate x1 x3 to xn all of them are fixed. There is a change in the function, differential change in the function when the coordinate x1, x2, xn goes to x1 plus delta x1, x2 plus delta x2 up to xn plus delta xn. The change in the function df can be written as this. So this is simple generalization of 1, 2 and then we can generalize it to n-dimensional functions. Okay? This is the simple rules for partial differentiation, which we will be using quite widely in this course. So you need to be very confident about the rules. Your conception must be very clear about the partial differential and its rules. Okay, now let us assume another. Let us start with another mathematical problem. Let us assume that we have three coordinates. They are x, y, and z. And we also have a relation, a mathematical relation that can be mathematically written as some function of f, x, y and z is equal to 0. So you understand the picture, right? So you have a three coordinates. So you can, so whenever you have this kind of problem, you should try to visualize the problem first. So you have three coordinates, x, y and z. So three coordinate you can visualize in three-dimensional coordinate space. 3 is very, I mean 3 is good now, 2 is fine and 2 is very good, 3 is okay and you can still visualize something, but above 3 you cannot do anything and visualization becomes poor. So this is your x coordinate, this is your y coordinate, this is your z coordinate. And this also says that there is a relation between x, y and z. So how you can visualize the relation of three coordinates x, y and z in a three-dimensional space? So the relation basically means a surface on this three-dimensional space, right? So there is a relation. One particular relation is corresponds to a surface. So this f, x, y, z equal to 0, this relation corresponds to a surface on this x, y, z plane. So this surface is essentially represented by f, x, y, z, some surface equal to 0. Okay. So now you can go back to the previous diagram what I have drawn. You can imagine the previous diagram, previous picture what I have drawn. I have drawn a similar kind of surface, right? In the previous diagram, I have drawn a similar kind of surface, and the picture in both cases the same. Was same. In that diagram, what I have drawn a two-dimensional function f, which is a function of x and y. In this diagram, I am drawing a surface, which is a surface of coordinate x, y, f, x, y, z equal to 0. I mean, the situation is same. In this case, what you can say that this z, I mean, this equation actually tells you that this z is a function of x and y, and this is that function. Both the situation are same. In this case, instead of writing this equation, what I can write z is a function which is a function of x and y. Or I can write x, which is a function of y and z. Or I can write y as a function of x and z. The thing is that from which direction you are looking. If I take my x and y as independent coordinates, then z will be a function of, I mean, consequence of this equation is z is a function of x and y. If I take y and z as independent coordinates, then consequence of this relation is x as a function of y and z. And if I look from other side, if I take x and z as an independent variable, my y will be a function of x and z. Okay, and all these three description is correct. I mean, I can always impart this equation. I can solve x for y and z, I can solve y for x and z, or I can solve z for x and y. Pictorially, you can look at this problem in this way. Now, what is the consequence? Let us assume that let us not take one particular representation, or I take my x is a function of x, y and z. Now, if I infinitesimally change y and z, y to y plus dy and z to z plus dz, then dx from the previous knowledge I can write down dx is equal to del x by del y at constant z dy plus del x by del z at constant y dz. Right? So infinitesimal change in y and z will give you an infinitesimal change in x, which is dx, which can be written by in terms of dy and dz with the slope. This is one particular description. I can, without using any generality, I can invert, I can solve that equation and write down y as a function of x and z, and do the same thing. I can change x to x plus dx and z to z plus dz and try to calculate what is the change in y. So that dy will be simply del y by del x at constant z dx plus del y by del z at constant x d of z. Okay, sir. Now these two are representing the same situation, same equation. There is no difference. I mean, all the changes are changes on these functions, right? So I am going one coordinate to another coordinate. That is, I am going from one point to another point on this function. Only thing is that out of this x, y, z, I know that a function is basically a constraint among this coordinate x, y, and z. Only thing is that what are the two coordinates I am choosing as an independent coordinate, and what is the one coordinate that I am choosing as dependent coordinate. So that varies. Otherwise, everything is fine. I am going from one particular point to another particular point, infinitesimally close on this surface. So they can be represented in these two. Now what I can do, I can substitute my dy from here to here. If I put this dy from here to here, so what I will do? I will have dx is equal to del x by del y at constant z, del y by del x at constant x dx plus, I will have this times this, so del x by del y at constant z, del y by del z at constant x plus, I have this quantity del x by del z at constant y dz. So I obtain an equation of this form.
So shouldn't be del y del x at constant z
Huh?
there in the first term?
Yeah, constant z. Sorry. So this is constant z. So now try to understand this equation. So I have three coordinates x, y, and z, and I have a relation f x, y, z. A function of x, y, z is equal to 0. So that means that out of these three coordinates x, y, and z, all of them are not independent. Two of them are independent and one is dependent. Now, whatever, which coordinate you choose independent, which coordinate you choose dependent is up to you. Let us choose that x and z, these two are independent coordinates. If I choose x and z as independent coordinate, then I can vary them according to, I can vary them independently, but y will not be independent then. So I am allowed to vary dx and dz independently. So this relation should hold for any arbitrary value of dx and dz. If this relation holds for any arbitrary value of dx and dz, what you can say? You can say that this should be equal to 1 and this should be equal to 0. Otherwise, this relation will not hold if I vary dx and dz arbitrarily. So this tells you that partial derivative of x with respect to y when z is fixed, and partial derivative of y with respect to x when z is fixed is equal to 1, and del x by del y constant z, del y by del z constant x is equal to minus by del z at constant y. So these two are very important theorem in partial differential calculus. If you will have several consequences, we will use these theorems quite heavily during this course. So let us, so what is, from here actually you can say that del x by del y at constant z is the same thing actually. It will be 1 by del y by del x at constant z. So this theorem you can write del x by constant z, del y by del z at constant x, then comes del z by del x at constant y is equal to minus 1. I mean, whatever form you want to write, you want to write it in different form. I can take this here from here because of this relation. So I know that del x by del z is nothing but 1 by del x by del z, which is del z by del y at constant. This consequence, I can take this from here to here as a consequence of this relation. Okay, so these are the two relations, two partial relations involving partial derivatives, which we will be using heavily in this course. Any question?
So this is Euler's relation, right?
Yes.
Okay, sir.
So you understand this, right? So it is important to understand the idea, the conceptual understanding about the partial differentiation. I mean, when you have multiple coordinates, which coordinates you want to differentiate, keeping which coordinates fixed, and how they are related. So these relations actually, this will be very powerful relation. I will come to that. I mean, in the context of thermodynamics, using this relation, how we can, do some simplistic measurement. We can predict something for a thermodynamic system. I will come to that. That is the next part of this lecture. I will discuss that. So what is the, where the powers of this equation lies. In the context, I will give you some example in the context of some specific thermodynamic system which you already know. Okay? Okay, so let us take a break for 20 minutes. Okay, then we will come back again. So this is 2:20. Let us meet at 2:40. Okay?
Thank you.
Okay, sir.
Hmm.